Hey everyone, and welcome. Today we are diving into something that's, well, it's absolutely fundamental if you want to write professional, high-quality code. We're talking about the 5 solid principles. Let's get right into it.
So let me just ask you something. You ever been on a project where you make one tiny little change and suddenly a dozen other things break? Or, when adding a simple new feature feels like you're trying to untangle a giant ball of yarn? We have all been there, and it is a total nightmare, right? Well, what if I told you there's a way out of that mess? That's where SOLID comes in. It's an acronym, SOLID, and it stands for a set of 5, let's call them thinking rules, that help you write code that's clean, way less buggy, and most importantly, super easy to change down the road.
And here's a super important point right up front. We need to be clear on what SOLID is not. It's not some framework you have to install or a library you add to your project. Nope, it's a mindset. It's a collection of principles that guide how you design and structure your code before you even type a single line.
All right, let's start breaking this down, starting with the first 2 principles, the S and the O. You can really think of these 2 as the bedrock, the absolute foundation for building any piece of solid software. First up, we have S for the single responsibility principle. And the idea here is beautifully simple, but so powerful. A class should have one and only one job. That's it. It should have one single reason to change. Think of it like a specialized tool. It does one thing, and it does that one thing perfectly. Okay, check this out. Here's a classic don't do this scenario. We have a student class that's trying to wear 2 completely different hats. It calculates a student's marks. That's business logic. But it also saves the student's data to a database. That's a data persistence job. And what's the problem? Well, if you change how the database works, you could accidentally break the mark calculation. The 2 are tangled together.
So, how do we fix this? Simple. We perform a little surgery and split them up. The student class now only worries about student logic, and we create a brand new student repository class whose only job is to handle the database stuff. And the payoff? Oh, it's huge. Each class is way easier to understand. You can test them separately, and you can change one without that constant fear of breaking the other.
All right, so we've got our first building block. Now let's add the O. This is the open/closed principle. It says our code should be open for extension, but closed for modification. Now, what on earth does that mean? It just means you should be able to add new functionality without cracking open and messing with old stable code that already works. Take a look at this code. We've all written something like this, right? A big chain of if-else statements to calculate salary based on employee type. But now, what happens when the business wants to add a new contractor type? Well, you have to go back in, break open that function, and add another else if. You're modifying tested working code, and that's always playing with fire.
Now for the much smarter way. We use one of the superpowers of object-oriented programming. We create a base employee class and then have our intern and full-time classes extended. Now, when we need to add a contractor, we just create a new class that also inherits from employee. We're adding brand new code without ever touching the old stuff. It's open to being extended, but closed to being modified. See?
Okay, the foundation is in place. Now for the next 2 letters, L and I. These principles are all about designing clear, logical, and predictable ways for all our classes to talk to each other.
So, L stands for the Liskov Substitution principle. I know, it sounds super academic and a little scary, but the idea behind it is actually really intuitive. All it means is that a child class has to be a perfect substitute for its parent class. It needs to be able to do everything its parent can do without causing any weird surprises. Put simply, a child must behave like its parent. And here's the classic example that makes this crystal clear. Let's say we have a bird class, and it has a fly method. Makes sense. Then we create a penguin class that inherits from bird. But hold on, penguins can't fly. So what does the fly method do now? Does it do nothing? Does it throw an error? Either way, it breaks our expectation. If you give me something that's a bird, I expect it to fly. The penguin breaks that contract. So how do we fix this logical mess? We make our design reflect reality. We can have a generic bird class and then a more specific flying bird class that inherits from it and has the fly method. Now, a sparrow can inherit from flying bird, but a penguin just inherits from the base bird. The rule here is simple. If your code's logic breaks real-world logic, your design is wrong. Full stop. All right, next up is the interface segregation principle. This one's all about not forcing things on our classes that they don't need. The idea is that it's way better to have lots of small, specific interfaces than one giant do-it-all interface. So for example, look at this. We have this big, fat interface called machine, and it says anything that is a machine must know how to print and scan. But now, what about a simple old-school printer? It can print just fine, but it has no idea how to scan. So it's forced to have this useless scan method that's either empty or throws an error. It's just awkward. The fix, as you can probably guess, is to segregate them. We create a small printer interface with just the print method and a separate scanner interface with just the scan method. Now, our simple printer can just implement the printer interface. And a fancy all-in-one machine, well, it can implement both. The result is so much cleaner, no more empty methods, no more confusion. And that brings us to the grand finale, the D. And honestly, this one might be the most powerful of them all. This is the real key to unlocking truly flexible, adaptable systems. D is for the Dependency Inversion principle. The big idea here is that your high-level, important modules shouldn't depend on the low-level, nitty-gritty details. Instead, both should depend on abstractions, like interfaces. In other words, your code should depend on abstract concepts, not on specific, concrete things. So how does this actually work? Well, instead of your main app directly using a MySQL database object, you do this little three-step dance. 1, you define an abstract idea, like a generic database interface. 2, you create your concrete class, like MySQL, which promises to follow the rules of that interface. And 3, you inject that abstraction into your app. Now your app only knows it's talking to some kind of database. It has no idea that it's MySQL under the hood. And you might be thinking, wow, that sounds like extra work. But trust me, the payoff is absolutely massive. Your code becomes incredibly flexible. You could swap MySQL for PostgreSQL tomorrow, and you wouldn't have to change a single line of your app code. It also makes your code 1,000 times easier to test and lets your whole system scale more easily. Whew! Okay, we made it through all 5 principles. So let's bring it all home and talk about the key takeaway you need to remember from all this. But before we do our final recap, I have to say something really, really important. Solid is guidance, not law. These are not rigid rules you must follow blindly in every situation. Think of them as a set of really smart guidelines from an experienced mentor, designed to help you make better decisions. Okay, so here it is, your ultimate cheat sheet. Let's lock it in. Ready? S, one class, one job. O, extend your code, don't modify it. L, a child class must act just like its parent. I, keep your interfaces small and focused. And D, depend on abstractions, not on concrete details. That's it. When you really internalize these ideas, you're not just learning rules. You're gaining actual coding superpowers. You'll be able to design cleaner, object-oriented systems. You'll avoid bugs before they even happen. You'll understand why professional frameworks are built the way they are, and you'll just write much more professional code. So I'll leave you with this question. Which one of these principles really clicked for you? Which one are you going to consciously try to practice in your very next piece of code? Because thinking about that and just picking one to focus on is the absolute best way to start making Solid a natural part of how you code. Thanks for joining me for this explainer.